Hi guys, welcome to another YouTube video. Today we'll be discussing matrices and simultaneous equations. Three simultaneous equations with three unknown variables, x, y and z. So here is a Cartesian equation of a plane with a, b, c being the normal vector. Now we can see the plane here. Imagine we had three of these equations with three different coefficients and we're trying to find the intersection basically, and we're going to delve into a bit of the geometrical interpretation of three equations. So guys, we have three equations of three different planes. We want to find the intersection point, if there is any intersection point, and from there we want to look at how the three planes interact with each other. So hopefully you guys know, using your knowledge of matrices, that these three equations can be reduced down to a matrix form and can therefore be simplified further. It'll be way better than elimination and substitution. So matrices, you'll find the inverse matrix, bring it to the other side and find your x, y and z. So that's what we're going to do now. We're going to reduce these down to a matrix form. Okay guys, so here is the matrix representation of the three equations that we have above. Now if you see, using matrix multiplication, we can see that, you know, we bring the 1 times x, 3 times y, minus 2 times z. And we get this equation, x plus 3y minus 2z, and then this will equal 7, right? And what we want to do is find the inverse of this matrix, and we want to times it by each other. Because a matrix times its inverse is the identity matrix, and any matrix times the identity matrix is itself. So this will turn into the identity matrix if we multiply the inverse times there. Therefore, we'll just get x, y, z on this side. Because we're doing it on this side, we have to bring it on this side as well. So we're timesing the inverse of this matrix by this. In order to find the inverse of this 3 by 3 matrix, we're going to find the determinant, and we have the cofactors here. So we have the number here, and we're going to find the determinant of this quadrant of the matrix, and then it goes plus, minus, plus this way, and you can do it down as well. So the determinant of this will be, okay, so it's going to be 1, and then here we'll have minus 2 times minus 1, 2, minus 1, which is 1. So it will just be 1 times 1, which is 1, minus 3. Okay, so we have minus 3 here. We're going to find the determinant of this. 2 times minus 1 is minus 2, and then minus 2 minus 3 is going to be minus 5. Yeah. And then we're going to see here we have minus 2. And then the determinant of this is 2 times 1, 2, minus 6. 3 times minus 2 is minus 6, so minus 6. So we have 2 plus 6, which is 8. And then this is going to be 1 plus 15 plus, minus 16, which is going to be 0. So what do we know about a matrix when its determinant is 0? It means it's singular. So in the context of this means that we cannot find an inverse, and there are therefore no solutions. However, we need to look at the consistency of these three equations. If the determinant is 0, either there are no solutions or there's an infinite number of solutions, and that all depends on the consistency of the equations. And we can see later on that you can form things like sheaves, triangular prisms. The planes can be parallel, so they don't intersect each other, or they can be on top of each other where they intersect indefinitely, therefore an infinite number of solutions. So guys, these equations are consistent, therefore they'll form a sheaf, which we're going to go on later to show. Because the determinant is 0, they're consistent, meaning the planes are coincident with each other. Okay guys, so what do we do when we know the determinant? Right, so we're going to find out when we have a system of linear equations, three linear equations with three variables, x, y and z. We're going to find out the geometrical interpretation of those three equations, which represent planes in the 3D space. Right, so we're going to look at the determinant of the matrix first. So that, and we're going to see, does the determinant of the matrix equal 0? If it equals 0, then there's no inverse. We're going to look at if the determinant is not 0. If it's not 0, what we're going to get is a unique point where all three of the planes intersect one another at one unique solution. So in that case, excuse my drawings, imagine this is a plane, this is a plane, this is a plane, they're all going to be intersecting at that point. Determinant equals 0. Well, as I've mentioned before, there will either be no solutions or an infinite number of solutions. It all depends on the consistency of the equation. If the equations are consistent, then what we're going to get is an infinite. Then we're going to get an infinite number of solutions. If it's not consistent, then we're going to get none, no solutions. So with this, the planes will be parallel to one another. Not coincident, parallel. They won't be intersecting one another at all, so they don't meet. Or if they're consistent, infinite. So we're going to get things like a sheaf, a triangular prism, or if we have two planes which are parallel and then one going through them. So a sheaf is when all the planes meet each other but on a line, only one line. Now I'm going to take you through an example question. Okay guys, so we have an example question here. We have three equations with three unknown variables. Now again, what we can do is transform this into a matrix equation. So we have down here 4 minus 5, 3. 3 by 3 matrix. And then 3, 3 minus 4, 5, 4 minus 6. X, Y, Z is equal to 3, 48, 74. Okay. Now what we're going to do, we're going to find the inverse of this matrix. We're going to bring it to the other side and then find X, Y, Z. And hopefully the determinant is not 0. If it's not 0, then we get one unique solution where all three planes meet. Alright guys, so I'm going to use a calculator. You can use the same method I did before finding the determinant. You guys know 3 by 3 matrices and the inverse. So you find the matrix of cofactors and then a transpose matrix of that, and then you divide by the determinant that you found earlier. Okay guys, so we have the inverse matrix here. We're going to multiply it by 3, 48, 72. Because remember, if we multiply the inverse by this, we get the identity matrix, and then identity times this is just this, and then whatever we do on this side, we do on that side. So we end up with X, Y, Z equals this inverse times that. This is going to equal minus 1, 7, minus 6, minus 18 times 48. So it's a big multiplication. I'll just do it for you guys quickly. Okay guys, so using the calculator, the answer is 8, 4 minus 3. The planes all meet at this single point. Okay guys, thank you for watching this video. Hopefully you understand a bit more about matrix multiplication when looking at and considering a system of three simultaneous equations and finding the values of X, Y, and Z, and what to do if the determinant is 0, and what that means for the equations and what it will look like when you graph it in a 3D space. If you guys have any more topics that you want to do, if you have any questions on this video, if you want to know more about matrix, like finding the inverse of 3 by 3 matrix, or if you want to know more about what we delved into about matrices in terms of planes, and look at how planes intersect one another, or if you want to do like mechanics, statistics, normal maths, let me know down in the comments below. Thank you.